Look at these functions. What we're going to do is to add them together, and we'll put their sum at the top, starting at the left like this. Adding them gives us this new function. And here's another function. And we can also add that. And here's another. This one's a very shallow curve, so it won't make that much difference when you add it in. But if you look closely, you'll see that what happens is that it just smooths out the ripples. So now we've got a function that looks rather different from any of the functions that we started with. What you've just seen is the addition of these four functions to finally give this one. Actually, this final one isn't quite as straight as this, but the wiggles in the graph are so small that they don't show up on a drawing on this scale. But it is quite remarkable how quickly, just by adding a few functions together, you can get very close indeed to this one. Let's just have another look at it. This idea of adding functions to produce new ones is very useful when you're trying to approximate to a particular function using other functions drawn from a specified set. Now, we've been looking at functions, but this program's part of the linear algebra section of the course, and that's all about vectors. But you've already seen that you can think of a function in terms of vectors. And that's what we're going to be doing today. We're going to be looking at a vector space of functions, and we're going to be considering a particular problem. But you'll see in the text that it's only one of a whole class of related problems. But what I want to do first of all is to give you a geometric image, a picture that you can carry in your mind when you're looking at these other problems, and that we'll be using time and again throughout the program. Basically, all the problems reduce to this. What we've got is a point P in a vector space specified by a vector P. And we've got a subspace. And the problem is to try to express as best we can this point P using only vectors in the subspace. It's a bit like the problem of two-dimensional man trying to get an interpretation of 3 space. Two-dimensional man would have a limited interpretation of 3 space in which his own world would be a subspace. His movements would be limited, confined to rotations and to translations in the plane of his own space. He's confined to the subspace of the plane, which he can't possibly get out of. So from this confinement, what possible interpretation is he going to be able to get of a point, such as this one, P, which is not part of his subspace? Clearly, he can only think in terms of his own subspace. But how close could he get to a point outside his plane? The closest he can get to P would be here, the perpendicular projection from P onto his plane. Now, I can take an outside view of the problem. This subspace is the world of two-dimensional man. Here's the point P. Q is the nearest the man can get to the point P, and Q is just the perpendicular projection from P down to the subspace. And clearly, that could be specified by a vector, which we'd obviously label little q. And then this vector, perpendicular to the subspace, will just be P minus Q. Now remember, what I'm trying to do is this. I'm trying to specify this vector Q. And to do that, we just look to see what characterizes Q, what's special about it. Well, what's special about it? That this vector, P minus Q, is orthogonal to the subspace. Now, to be orthogonal to the subspace means it's orthogonal to every vector in that subspace. So I could pick a couple of vectors. I could call this one, say, v1, and have another vector, v0. And since this vector, p minus q, is orthogonal to the subspace, it's orthogonal to v0 and to v1. Now, that's something that we can express algebraically, because two vectors are orthogonal if their dot product is 0. That means we can now express the condition on Q algebraically by two equations. These two equations simply tell us that P minus Q is orthogonal to V0 and it's orthogonal to V1. Now, we can go one step further. We can express Q like this as a linear combination of the two vectors V0 and V1. In other words, what I'm doing is to use V0 and V1 as a basis for my subspace. Then what I've got to do is to calculate these coefficients A0, A1. As soon as I know those, then I'll know the vector Q. And all I've got to work with are these orthogonality relations. So just how do I use those orthogonality relations to calculate A0 and A1? Well, here's Robin.
Well, these coefficients A0 and A1 are very important, and we're going to spend some time looking at them. They're actually called Fourier coefficients after the French physicist Joseph Fourier, who introduced them while looking at the conduction of heat. Well, how do we calculate them? We calculate them using the orthogonality relations that Norman told you about. Here are the orthogonality equations, and we want to calculate A0 and A1. So let's start off with the first orthogonality equation, and that's going to give me A0. I've written out some of the calculations already, so let's go through the steps. First of all, we rewrite this in this form, P dot V0 equals Q dot V0. And then we can actually substitute in this expression for Q, Q dot V0. We now expand this dot product to give two terms. Here's the first term corresponding to this, and here's the second term. So this is all equal to P dot V0. Well, that equation holds for all bases, V0 and V1, but as you remember, we can often simplify calculations by taking orthogonal bases. So let's make V0 and V1 orthogonal and see what we get. If V0 and V1 are orthogonal, then this dot product is just 0. And we're left with this. And we can calculate A0 just by dividing by this. So A0 is this over this. A0 equals P dot V0 over V0 dot V0. So that's A0, which we found by looking at the first orthogonality relation. And the obvious thing now to do is to look at the second orthogonality relation, and that'll give us A1. We can go through the same sort of calculations, and we end up with a very similar answer. What we get, in fact, is that A1 is equal to P dot V1 this time over V1 dot V1. A very similar sort of equation. So that's the Fourier coefficients A0 and A1.
Now, as I've already hinted earlier, Fourier coefficients are very important because they crop up in a whole variety of circumstances, but they always crop up in much the same way. What you're trying to do is to approximate to a vector P using a vector Q and an orthogonal basis. What we've got to do now is to apply that idea, but to make a conceptual leap, because we want to go back to our original problem, which you remember was posed in terms of functions. But I want us to keep in mind our original geometric image that we had. Now this time, you've got to free your mind and use your imagination, because although this looks very geometric, I want you to think of this subspace as being a subspace of functions. And what we're on about now is trying to approximate to a given function P by a function Q in this subspace. Now, if we're to use the same ideas that we've been developing so far, that means that we've got to find two functions, V0 and V1, which are orthogonal, which we're going to use as a basis. Well, that's fine. It sounds very easy, but what do we mean by orthogonal functions? How can we talk of two functions as being orthogonal? we've already met the idea of a vector space of functions, but so far we've not had a dot product of functions, so we can't really talk of functions being orthogonal. So that's our next step. We've got to try to think what we could mean by the dot product of two functions. If we could do that, then we could interpret these relationships where P, V0, and V1 are all functions. But just how do we define the dot product?
Well, if f and g are functions, we define their dot product like this. F dot g is got by multiplying them together and integrating from minus pi to pi. So, for example, if f of x is x and g of x is x cubed, then the dot product f dot g is the integral of their product x to the fourth, and that's just 2/5 pi to the fifth. And now we know how to define the dot product, we can say when two functions are orthogonal. That's when their dot product is 0. And an important example of that we've got here. If f is 1 and g is cos x, then these functions are orthogonal. Why is that? Because f dot g is the integral of 1 times cos x, and because we're integrating from minus pi to pi, this integral is just 0. So we can use the functions 1 and cos x as an orthogonal basis. They're orthogonal, so let's use them as our basis, and we'll use them for v0 and v1. And remember, we've got to find the function q, which most closely approximates p. So v0 is 1, v1 is cos x, and for the function p, we're going to take mod x. That's a v-shaped function that you saw at the beginning of the program. So what we've got to do now is to find the corresponding Fourier coefficients, a0 and a1. Well, let's look at a1. We've got to calculate p dot v1 and v1 dot v1, and p dot v1 is just this integral of p times v1. v1 dot v1 is just the integral of cos squared. So a1 is just this quotient of integrals, and if you work it out, what you get, in fact, is minus 4 over pi. And we can do exactly the same thing for a0. It's a quotient of integrals, and if you actually work out these integrals, then the answer turns out to be pi over 2. So we now know a0, a1, v0, and v1, and we can put them all up here to give us q. And this is what we get. Q is pi over 2 minus 4 over pi cos x. And that's the closest approximation we can get to the function mod x by taking a linear combination of 1 and cos x. Well, let's now see how good an approximation it really is. This is the function mod x from minus pi to pi. And this is the function cos x from minus pi to pi. Notice that both functions are symmetrical about the y-axis. Multiplication of the cos x function by the Fourier coefficient minus 4 over pi gives this function. And if we want to approximate this to the mod x function, we need to translate in the plus y direction. The best overall approximation is when the translation is through plus pi by 2. So the best approximation we can now get for mod x is pi by 2 minus 4 over pi cos x. This is the closest we can get to mod x as a linear combination of the orthogonal functions 1 and cos x.
Actually, that wasn't a very good approximation to mod x because we only used two functions, and we could do a lot better by using more. In other words, going to a higher dimension. You see, what we've done so far is to approximate to a vector by using vectors in a two-dimensional subspace. Now, we've already generalized this model so that we can think of our vectors as representing functions. But what we're going to do now is to generalize it in another way. We want to go back and think of these vectors again just as geometric vectors, but think of this model as existing in a much higher dimensional space. We want to think of this subspace as being, say, of dimension 4. Now, it doesn't look like it, but don't worry. Just think of this as a space of dimension 4. If that's the case, then we could find 4 orthogonal vectors in this space, v0, v1 as before, and then we could have another couple, v2 and v3. That gives us 4 orthogonal vectors. Now, they don't look orthogonal, but then this doesn't look like a four-dimensional space. It's not an entirely non-trivial idea. So don't worry, just use your imagination and just relax and enjoy it. Just think of these as four orthogonal vectors. If you do that, then we can express our approximating vector q like this, as a linear combination of the four orthogonal basis vectors. And you can go through just the same routine argument as before and calculate the coefficients. A0 and A1 as before, A2 and A3 are given by very similar formulae. Now, if you can get hold of that, then you're there. You've got a very big idea within your grasp, because having extended to 4 dimensions like that, you can follow through exactly similar procedure and, in fact, extend to any number of dimensions you like and get an approximation vector q in a subspace of any dimension. And it turns out that the coefficient is given by exactly the same sort of formula. AR is just given by this, and you should be recognizing this pattern by now. So that's the rth Fourier coefficient. And remember where these came from. Really, we've got two lots of orthogonalities. First of all, the vector p minus q is orthogonal to the approximating subspace. And then within that subspace, we've got an orthogonal basis, so that the basis vectors form an orthogonal set. So v0.v1 is 0, v1.v2 is 0, and v0.v2 is 0, and so on. And vm.vn is equal to 0 whenever m and n are not the same. So that's the situation we've got, and you see we're now in a situation to actually calculate Fourier coefficients for approximating vectors in any subspace of any dimension you like. All we've got to do now is to interpret this idea in the particular case when we are approximating functions.
Well, how does that work with our example where we're trying to approximate the function mod x? Do you remember we started off with the basis vectors 1 and cos x, but as Norman's just told you, you can get better approximations by taking more basis vectors, v2 and so on. Well, the basis vectors we're going to take are v2 equals cos 2x, and in general, vr equals cos rx. And why do we take those? Because they're all orthogonal. You can show that any two of these cos things are orthogonal. Cos mx dot cos nx equals 0 whenever m is not equal to n. You can check that just by doing the integrations. Well, how does this work for our model? Here's p, that's the function mod x. Here is q, and we're working out q in terms of all these new basis vectors. 1 cos x, cos 2x, cos 3x, and so on. So what we've got to do now is to calculate the Fourier coefficients AR and then calculate q. This is the general summation series for q. So now we need to find a general expression for AR of VR. Remember, AR equals P dot VR over VR dot VR. So this is the general expression for the rth Fourier coefficient. Now in our example, VR and P represent two functions, cos Rx and mod x, respectively. In terms of our definition of the dot product of two functions, our general expression for AR becomes an integral representing P dot VR divided by the integral representing VR dot VR. So with this expression for AR, we can calculate the Fourier coefficient for any value of R. A0 equals pi over 2. A1 equals minus 4 over pi. A2 is 0. A3 is minus 4 over 9 pi. A4 is 0 again. And we carry on in this way until we get a whole set of coefficients. We can now use these coefficients in our original expression to give this, a summation of these terms, each one being a product of a Fourier coefficient and a corresponding element of the set of orthogonal functions. For example, for this term, the coefficient is minus 4 over 49 pi, and the function is cos 7x. So this is our expression for q, approximating the function mod x. Let's see what it looks like. This is the function mod x. And this is a first approximation, pi over 2 times the function 1. A function orthogonal to this is cos x. Multiply by minus 4 over pi, the Fourier coefficient. Adding gives a better approximation. It's the one we had before. The next function with a non-zero Fourier coefficient is cos 3x. Minus 4 over 9 pi is the coefficient. Adding as before gives an even better approximation. And we can keep going with additional orthogonal functions. These 5 terms give this approximation for mod x.
Now, this idea of approximating to a function by a set of orthogonal functions really is one of the big ideas in mathematics and one of the most powerful techniques in mathematical physics. And I must say, it's one of my favourite topics in the subject as well. And it's interesting to notice that although it is so important, we've got to it by a fairly simple and straightforward extension of our ordinary linear algebra techniques. Straightforward, but perhaps with a liberal use of our imagination, but never mind, that's what mathematics is about. What we've done is to start with this particular problem, remember. We had a point, P, a subspace, and the problem was how to find a point in that subspace which gives us the best approximation we can to the point P.